Here's some help with the trig identity proofs. Prove a couple questions for you. From your textbook number 9. You want to show that the left-hand side equals the right-hand side. So let's first change everything to sine and cosine. Change secant to 1 over cos. On the left side and the right side. Now I want to get rid of the denominators, so I'll multiply everything, both sides of the fraction, top and bottom, by the lowest common denominator, in this case cosine x. And it turns out that that just happens to be the same common denominator on the right-hand side. So cosine times 1 over cosine is 1. And I'll leave the bottom factored. Okay, so my left-hand side is about as simple as I can make it. On the right-hand side, cosine times 1 over cosine is 1. Cosine times 1 is cosine. And sine squared times cosine is just sine squared cosine. Okay, and now we're kind of stuck because it's about as simple as it can get. But I recognize that there is a 1 plus cosine in the top on the right-hand side and a 1 minus cosine on the bottom on the left-hand side. So when I get to a point where I'm stuck like that, I see that there's conjugates on either side of the fraction. On either side, I'm going to multiply one of the sides by the complex conjugate, or by the conjugate. So I'll take 1 plus cosine x, which is the conjugate of 1 minus cosine x, and I'll multiply that by the top and the bottom of the fraction. And what's nice about that is now I've got the 1 plus cosine x on the top. I have this factor of cosine x that I'll just put in brackets there. That's the same as this one. And now somehow, when I put these two together, I should get sine squared x. So let me FOIL out this expression. So first times first, 1 times 1 is 1. Outsides, negative cosine x. Insides, positive cosine x. And last, negative cosine squared x. So the negative cosine and the positive cosine will cancel. So in the denominator, I'm left with 1 minus cosine squared x. Now because sine squared plus cosine squared is 1, 1 minus cosine squared x is the same as sine squared x. And there it is. Done. So on to question number 23. So question number 23, we want to show that tan x times cosecant x plus 1 is equal to cotangent x over cosecant minus 1. So actually you made a typo here. There should be an x right after the cosecant. We want to show that the left-hand side is equal to the right-hand side. So the first thing we can do is change everything to sine and cosine. So instead of tangent, I'll write sine over cosine. And instead of cosecant, I'll write 1 over sine. Now on the right-hand side, I have cosine over sine in the numerator. And the denominator is 1 over sine minus 1. So on the right-hand side, I'm going to take that lowest common denominator and I'll multiply the top and the bottom of the fraction by that sine x. And when I do that, sine x times cos over sine is just cosine. Sine x times 1 over sine is 1. Sine times 1 is sine x. And that simplifies it nicely. On the left-hand side, I'll expand this expression. So when I do sine over cos times 1 over sine, the sines cancel, leaving 1 over cosine. And sine over cos plus 1 is just sine x over cos x. So this is 1 plus sine x over cos x. Oh no! They're both in simplest form, but they're not at all like each other. So I do see that I have 1 plus sign in the numerator on one side, 1 minus sign on the denominator on the other side. So now I can choose either side to multiply by the complex or by the conjugate. So I'm going to take the right-hand side this time, and I'll multiply by the conjugate, which is 1 plus sine x, on the numerator and the denominator of that fraction, leaving me with cosine x times 1 plus sine x, and then I'll FOIL out the bottom. So I get 1 plus sine x minus sine x, and negative sign times positive sign is negative sine squared x. So again, the middle terms cancel, leaving me with 1 minus sine squared x, which is wonderful because 1 minus sine squared x is the same as cosine squared x, because sine squared plus cos squared is 1. So I'll write cosine squared x instead of 1 minus sine squared x. And then one factor of cosine can cancel from the top and the bottom, leaving me with the same thing as the left-hand side. Okay, so I had to multiply by the conjugate in order to solve that problem. Now, question 25. This one you need some extra space for. And there's so many different terms. That what I like to do for a question like this is do a substitution. Because otherwise it's just so complicated to keep track of all the sines and the cosines. So what I like to do for something like this is I'm going to say maybe let cosine x equal the letter A. I'm going to let cosine y equal the letter B. Sine x can be C, and sine y can be D. Okay, I don't really need a right-hand side for this one. I need a really big left-hand side. And I know my right-hand side is just 0. I can't change that. So I'm going to put in my A's and B's and C's and D's for this problem. So cosine x is A, cosine y is B, sine x is C, sine y is D, sine x is C, sine y is D, cos x is A, cos y is B. That's much easier to look at. So now in the denominators I have 2 binomials. So what I want to do with these 2 different fractions is combine them into one big fraction. So I need a common denominator, and that's going to have both of the 2 binomials in it. So it's going to have A plus B and C plus D. So the second fraction I'm going to multiply by C plus D. On the first fraction I'll multiply by A plus B. On the top and the bottom. That'll give me my common denominator. So I'll FOIL out this expression. A times A is A squared, A times negative B, B times A is BA, and B times negative B is B squared. I'll do the same thing for this one. C times C, C times D, negative D times C, and negative D times D. Now luckily, AB and BA are the same thing, so we've got positive BA, negative AB, those cancel. Positive CD and negative DC will cancel. So now I have A squared minus B squared plus C squared minus D squared. And then I have A plus B times C plus D in the denominator. Okay, so now I can't really factor much. I'm going to put my sines and cosines back again. So A is cosine x, B is cosine y, C is sine x, and D is sine y. I'm not going to expand the denominator because most times you really don't have to expand the denominator. You want to be able to cancel common factors if you find any. So I'll just put these cosines and sines back again. Now I recognize that I have cosine squared plus sine squared. Cos squared plus sine squared is 1. And now I'm left with 1 minus cos squared y minus sine squared y. And my denominator stays the same. Now because sine squared y plus cosine squared y equals 1, if I have 1 minus, if I move the cosine squared to the other side, 1 minus cosine squared is the same as sine squared. So I'm going to take that 1 minus cosine squared here, and I'll replace it with sine squared. So sine squared y minus sine squared y is on the top of my fraction. The bottom stays the same. And sine squared minus sine squared is 0. And 0 divided by anything is 0. So 0 equals 0. We're done. Now I'll also explain question number 26, just in case you missed that in class. Explain that one more time. We're trying to prove that cosecant squared of pi over 2 minus x minus 1 is the same as tangent squared. We'll go left-hand side, right-hand side. So tangent is the same as sine over cos. Tangent squared is sine squared over cos squared. Cosecant squared is the same as 1 over sine squared of x. Okay, and 1 over sine squared is really the same as 1 over sine pi over 2 minus x, all squared, and then minus 1. So really, I want to know what is sine of pi over 2 minus x? So I'm going to think about my transformations unit. This kind of looks like a transformation. A little side note here. So sine of pi over 2 minus x. This has problems because, first of all, the x has a negative 1 in front of it. So first thing I'm going to do is factor out that negative 1. So let me take out a negative 1 and switch the order here. So when I take x, negative x, and divide by negative 1, I have positive x. When I take positive pi over 2 and divide by negative 1, I'm left with negative pi over 2. So this is the same as a sine function. So if I take my basic sine, which starts at 0, 0, going up, comes back down, back again in 2 pi. And the negative 1 is going to reflect it in the y-axis. So if I had sine of negative 1x, then that would be a reflection in the y-axis. The minus pi over 2 is going to move my sine function to the right 90 degrees, or pi over 2. So this is 360 at the end, 180 is halfway, and 90 is 1/4 of the way through. So if I do sine of negative 1 x minus pi over 2, I'm taking that graph and translating it 90 degrees to the right. So now my maximum is at 0, 0, 1. And if I continue this graph, that And it's starting to look like the graph of cosine, which starts at the top. Okay, so sine pi over 2 minus x is actually the same as cosine. You take a sine graph and reflect it and then move it 90 degrees to the right, it looks exactly like a cosine. So instead of sine pi over 2 minus x, I'll write cosine x. This is 1 over cosine x squared minus 1. Which is the same as 1 over cos squared x. So now I want to make a common denominator, so I'll change the number 1 to cos squared x over cos squared x. So I can add those two fractions, and I get 1 minus cos squared x over cos squared x. Now 1 minus cos squared x is the same as sine squared x, because cos squared plus sine squared is 1. And now I've got the right-hand side. And that is how you prove trig identities.